Hello, my name is Sean Barnes. I'm going to be giving my presentation on a lunar mission. So the original idea that I wanted to do for my honors project was to model wings and aerodynamic surfaces, since I'm planning on doing aerospace engineering. And so my professor said no to that one. Personally, I think it's probably a better idea, since that's how you model aerodynamic surfaces in the real world. So I think I dodged a bullet with that. So instead, my second choice for my project was to focus on the physics of rocket design, and that one was approved. So I got to start designing a rocket. So to design a rocket, use the thrust equation. The problem with the thrust equation is, with the knowledge I currently have, I cannot solve the thrust equation. And because of that, the reason for that is I have to take all these classes first to know how to do these things, which I was going to make a joke about there being a UCSD admissions counselor assigned, but there's barely an audience, so oh well. So a lot of stuff that I don't know how to do. So fortunately, NASA has a rocket nozzle generator, and that makes my life significantly easier, since it gives me all the values I need to design a rocket. And I designed a really nice rocket. But of course, it's not really much of a project. So I instead decided to do a project on lunar orbit simulation. So in order to simulate an orbit maneuver, the equation known as the rocket equation is used. So I used this particular version of the rocket equation, which is the right one on the bottom in the red, because that one is easy to take from the NASA rocket nozzle simulator. And that uses 4 different variables. The first one, ISP, is what's known as the specific impulse, which is basically how efficient an engine is. And that's the one that I got from the NASA rocket nozzle simulator. The second one is standard gravity, which is just gravity at Earth's surface. And despite being an Earth's surface, it works everywhere. You can do it on the moon, you can do it around Mars, you can do it right on the sun if you really wanted to. And it's still the same value for that. The third one is what's called the mass ratio, and that's the mass of the full rocket stage divided by the empty rocket stage without the fuel, and that's put into a natural logarithm. And then finally, all those values are used to find the delta V. So delta V is pretty much the fuel tank for your rocket, and maneuvers are often done using as a reference, in which the initial velocity is the tangential velocity of your orbit at your first point, and the final velocity being the tangential velocity of the orbit at the second point. And that's commonly used instead of how much energy the rocket has or how much fuel, since it's a lot easier to do math around that. So there are 2 different methods that I found to find delta V. The first one is the equation on the left over there, which is what's called a Hohmann transfer. I had originally known what this is from a game I used to play when I was younger called Kerbal Space Program, which is basically a spaceflight simulator. Though unfortunately, I cannot find an easy equation for that on any academic source, though I did find an easy equation for it on Wikipedia, which provides the issue of it, being a Wikipedia source. It's generally not good for academics, but I'll deal with that later. The second one I found is more general, to find that's a way to find the tangential velocity of an orbit at the periapsis, which is the lowest point of the orbit. And that's found using the angular momentum on the top, and then the radius and the mass of said orbit. Now, to solve that dubious sourcing issue, I found 2 different sources to back it up. The left one is a orbit simulation that is on a program called Octave, which is an open source clone of MATLAB, which is a common simulation software used for a lot of engineering applications, in which that gave me a value very close to the one I calculated. And additionally, the one on the right is from a study by the European Space Agency when they were trying to do an independent lunar mission for themselves. And both of them gave me roughly the same value as the one I calculated, which was 3,131.9 meters per second. Now, one issue is, while this does work for the going from low Earth orbit to the transfer orbit, it does not work when you are entering the lunar orbit, because the lunar orbit is a hyperbolic orbit, meaning that it's like 2 parabolas next to each other. And because of that, the velocity equations do not work. So the solution to that is I decided to research the differential orbit equation. So the differential orbit equation was found by a mathematician named Binet, hence the name, who noticed that if you set a dummy variable of u to be equal to 1 over r, it makes it very easy to write out an equation that can be used to determine the shape of any kind of orbit. And this is for various different kinds. You can use it for obviously gravitational orbits, which is what I'm using it for, but can also be used for things like molecular orbits and other objects that have that kind of phenomena. So the equation in question is what's called a non-homogeneous second order differential equation, which means it has a second derivative as part of its function, and there are values of u on both sides that are variables. So additionally, there's also two constants. The first one is mu, which is called the reduced mass, so an orbit body is calculated, it's what's called a two-body problem, in which it's the interaction of two objects of mass and how their forces interact with each other. But because there's such a massive difference between the spacecraft and the moon or Earth, it effectively means that the mass you're using is basically just the mass of the spacecraft. But if you're comparing to more similarly sized bodies, such as Pluto and its moon Charon, that would give you a mass somewhere between those two. And then additionally, the angular momentum is also used, which is the L. Unfortunately, this equation can be simplified. So gravitational force is what's known as an inverse square law force, which basically means it gets exponentially weaker the farther away you get from the point of the force being exerted. And a force like this is what's known as a conservative force, which means it's path independent, and regardless of how you get from one point in the orbit to another, it'll always be the same force. And so because of that, I can use that top equation with f of 1 over u equals ku squared, in which the k is a modified version of the Newton's universal law of gravitation, which is used to solve the differential orbit equation. And then when I plug that in, I get the simplified equation below that, which I can solve using traditional methods of solving differential equations. And when I solve that differential equation, I get this monstrosity, which is why the coordinate translation was used in the first place, because it allows the equation to be solved in a significantly more simple manner and then converted back into it being in terms of the radius r. So, and also there is the value of psi, which is in the parentheses, because orbits are in spherical coordinates, and when they calculate orbits, they often use the theta that you traditionally use for cosine functions as the inclination of the orbit. So the textbook I found on this used psi instead. Then additionally, you can notice there's two cosine functions in there, and that's pretty much what gives the orbit its, I guess, curvature of the shape. And the nice thing about this equation is as long as you have the r at the periapsis, the angular momentum, and the reduced mass, you can pretty much use this for any orbit of any body around any other body. So it has very wide applications that you can use beyond just a simple lunar orbit. And now to model the trajectory, I just have to have these four values, which are all right there. The one small issue is I get this horrific abomination. So generally speaking, orbits are, curvish and all that. That one's a straight line. And so generally speaking, when you have a orbit going around a body from a interplanetary trajectory, which is kind of like the one I have, as an eccentricity of 1 or 2. This one's 502.8, which is a little bit much. And then it's at the periapsis point, it's traveling at 47,911 meters per second, which for reference, lunar escape velocity is 2,380 meters per second. So that's over 20 times as fast, which is a little bit too fast for my spacecraft to get there. The reason for this is was known as a sphere of influence, which is pretty much how much the distance that a orbital body can exert a force. And once you get past that sphere of influence, the force is basically negligible, and it doesn't affect the orbit of the spacecraft or an asteroid or anything else around it. So the issue is when you're traveling between spheres of influence, the conservation of angular momentum, which is due to being gravitational force, technically no longer applies since you're now having different forces act upon it, which depends on where it is, which basically means I cannot use the same angular momentum from outside, which means I have to find a way to fix it. And to find a way to fix it, I did what was called finding the equivalent hyperbolic orbit. So when I had this dilemma, I asked my physics professor what I should do, and he suggested that I try using the elliptical orbit that I used for my first orbit with the moon as a foci and see how close that would get to an actual lunar orbit in real life, which is a really nice way of saying that I'm fudging numbers. With the argument being that since the ellipse is traveling outside the sphere of influence, that would effectively make it the hyperbolic orbit. So this doesn't really work in real life. So it could make an astrophysicist sad if there was one in this audience, but I won't. Anyways, when I graphed all those orbits, that's pretty much what it looks like. And all those were graphed using the differential orbit equation, with the purple circle being the sphere of influence and the red one being the moon. So when I did the delta V values for all of these different orbits, for the first one, I got, as I said, 3,131.9 meters per second, which had a percent error of 1.05%, which I'd say is fairly accurate. The second one, which was based on the slowing down from the hyperbolic orbit to the lunar orbit, was negative 629 meters per second, the negative being because that's slowing down. And that had 25.12% error, which obviously that's very bad. So when I saw this, I decided to see potentially what I could do to make this value get closer to real life. So the first thing I tried was the ESA study mentioned that that they calculated their value from subtracting the velocity of the moon around Earth by the velocity of the spacecraft at the point of interception. I tried that, and that was what I got in the orange orbit, which is better, but still had over 20% error. So the second idea, which I thought of, was that I would take the escape velocity of the moon and subtract that by the velocity of the spacecraft when it enters lunar orbit. And for that, I got the blue graph, which for that, I got an under 1% error, which, beyond bad, that's significantly more accurate. And if I was to do this experiment again, I would probably see if that holds true on other orbits. So my hypothesis was technically wrong in that regard, but that's kind of science for you. And then the total delta V I got was 3,761.6, which is a 4.53% error from the ESA study I mentioned, which isn't terrible. And with all that, I can now design the rocket. So this project is for my differential equations and physics honors classes and not for any engineering class. So I'm just going to be showing off the basics of all these things, just so you know that they're there. So satellite. This is the rocket engine. I designed it in a software called SolidWorks, which is used for a lot of engineering applications. And that allows me to get the mass of the engine. And I can also find things such as the moment of inertia, where the center of mass is. I can also do materials, figure out density. And I can also, if I really want to be accurate, I could do heat simulations and force simulations, but I didn't really do that for this project since that was the focus. And then to find the fuel volume for the rocket, I used these two integrals, which in hindsight, I could have done the Calc 3 honors course and had a nice shiny H using these kind of things, but I didn't think of that last semester, so oh well. And then use these two with those shapes to get the total fuel volume. And then once I get all those, I can slap it into that very large complex fraction, and that can find the mass ratio, which is 3.23. And so now that I have all the values, I can multiply the specific impulse, which is 413 seconds, the standard gravity, and then the natural logarithm of the mass ratio to get the final delta V of 4,748.8 meters per second, which has over 987.2 meters per second of margin over the mission requirements, which gives me plenty of room to account for all of my calculation error. And then the end. And also all the sources, and special thanks to those people. So to David Havig, who's my physics professor, who helped me with figuring out my project and a lot of the physics behind it. Special thanks to Professor Sean Ferosian, who convinced me to basically double dip 2 honors projects into 1 honors project. And then to Britton Belford of Purdue for checking out my work. She's the reason I figured out that error thing. And also to Maricosta College for giving me the opportunity to do this project and presentation. If anyone has any questions, yeah.
What was your favorite thing that you learned in doing this project?
I feel like a lot of it was the fun of kind of the problem with all the lower division engineering stuff is you're not doing any actual engineering. It's just a lot of calculus and physics. But it's nice to actually see like this is how you apply it in real life, and kind of being able to combine the math, the physics, and all the design aspects, and actually figuring out this is what I actually need the physics and the math for, besides just to know it. Which I feel like that's what made it a lot more enjoyable, and it's probably the most enjoyable thing I did this semester on my classes, even though it was a lot of work. Else?
So if you could do the project over again, I think one area of improvement that you mentioned yourself would be sorry, I'm only in calculus 1 right now, so I'm like.
I had to squeeze a lot into this. I had to squeeze a lot into this presentation. I didn't have to cut a lot of stuff out.
You said that you were kind of fudging numbers.
Yeah.
Can you explain, like, if you were to do this project again, like, how could you, like, base your numbers more in reality, I guess?
So I guess if I go back to here is what I was thinking of in my conclusion was pretty much what I did based on the escape velocity, which that's more just physics. So pretty much for us, I guess, pictures. So this is the moon, sphere of influence. Pretend this is a circle around a circle. And then spacecraft orbit. So the escape velocity of this sphere is a value. And then the velocity at this point where it intercepts said, well, at this point where I want it to be, I pretty much, this picture is terrible. That was next. Pretty much what my idea was, if I was to try this again, is basically see if my idea of the velocity of my spacecraft at this point outside the sphere of influence and subtracting that from the escape velocity of the moon or any other body, see if that theory holds up in real life pretty much, rather than just this one nice instance where it gave me a really low error, which is one of those things, if I had more time, I would probably explain that a bit better, but
Good question.
Yeah.
How do you keep your rocket from getting maybe this is the whole point, but how do you keep your rocket from getting too close to the moon and then?
So the technicals of that is more the rocket science part, which I didn't really get too much into, but the one that was the most accurate was the one going from Earth's orbit to the flyby of the moon. That one I was able to get really close to accurate, but usually in real life what you do is if you're a bit off, you'd basically be this another one of these great images that I probably shouldn't be doing, but oh well. So if you're going from here and you're going into here and you don't want that, what you can do is you can basically, let's say you're right here and you have your nice little rocket, you can pretty much fire the engine and then that causes it to go a bit farther, and then you go like this, which is basically why you build in fuel margin, because you want to make sure you can do extra maneuvers to basically correct your course if you have any error in your measurements.
Okay, and then you can determine how far away you need to be just using Newton's.
Well, technically they use a lot of like guidance systems, and that's super complicated, and that's not what I'm going to be working with, so I can't really give you a good explanation of that. But that's the physics of what you'd actually be doing, pretty much.
So you have some extra fuel.
Yeah, I had way too much extra fuel. You can't say no to extra fuel.
So you want to be a aerospace engineer or a rocket scientist or?
Well, aerospace engineers, that's half of them do rocket science, half of them do planes.
Okay.
So
what do you want to do?
I'm still 50-50.
Okay. Keeping the options.
Most people aren't even narrowed down to being that specific, so I shouldn't be complaining too much. But
So would this work on different like planets, like and different moons, or?
yeah. So the rocket, the orbit equation here, as I said earlier, I can, as long as I know basically the lowest point of the orbit, the mass of the spacecraft and the body I'm around, and then the angular momentum, I can basically get any orbit around any body in a two-body system. So if it's like something really complex or it's like multiple moons and they're all exerting force, it wouldn't really work on that. But basically, you can go anywhere in the solar system with this without any real issue, as long as you know the numbers. So it is a lot of general application in that regard.
So this is a little off topic, but would you want to be like an astronaut?
I mean, if they told me they were going to strap me up there to do science, I'd say yeah.
Okay.
Like I very much just have very much a disdain for the space tourists and the people who pay large amounts of money to go joyriding. I think you should be focused on science, not that stuff.
Right. Because that's a lot of fuel, and that's like bad for the environment. Is that true?
I mean, it depends
Like,
on
how
what
much fuel are we actually using? Because I know like plane flight is
well,
like.
it very much depends on what you're using. Like, if technically, like what the space shuttle used was a hydrogen. Well, there's the solid rocket boosters too, but if we ignore that, hydrogen and oxygen just gives you water, and that doesn't give you any pollution.
Right.
This one used those two. So technically speaking, there were zero emissions. But like if you're burning, say, methane as your fuel, or what's called RPO1, which is a highly refined kerosene, there's some countries like China uses a lot of really toxic rocket fuel still, though they're moving away from that. It's like the kind of thing where like they have to quarantine the entire area if a rocket stage crashes onto someone. It's like it very much depends, but.
Well, thank you very much for your presentation. Very informative.